So I'm Laurent Socal from Italy, and now we are dealing with the part about the energy performance calculation of heat pumps in the context of building energy performance calculation. So we will start from some information about the context, which is important. So an emerging concern is setting up requirements to calculate and to display the building energy performance. So in every time you have to do something like this to display an energy performance, you need a meter and you need a benchmark. And typically the meter is your calculation method, and the regulation typically will provide benchmark so that you can rate your buildings against your scale. And it is very important that this meter is well known and is reliable, because if you change the meter, you're actually changing the requirements. So we are dealing now with the heat pump calculation within this context of a building energy performance calculation. And the building energy performance calculation is a complex system because you take into account the actual or specifically designed building envelope geometry and properties, and you take into account the actual specifically designed properties of all your system to provide comfort, and of course a standardized climate and use for regulatory purpose or actual data for audits, and you calculate the overall energy performance. This makes a huge calculation procedure. And here you have an example of the organization of such a procedure in the ISO environment. So you need some standards and calculation methods and assumptions that concern heat gains, the building fabric, climatic conditions, the condition of use of the building. You calculate first the envelope, typically, and you calculate the building needs for heating, cooling, and the needs for domestic hot water. Then you go through the systems, and you can see each one of these numbers is one standard or one calculation module. And heat pumps is just a small part here, but a very important part. And this is very important because you will see that product testing, product rating, and building rating has different requirements. So needs different kind of information about the heat pump, and this makes things a little bit difficult currently. So this is what is, there is a lot of work in progress in this field. In the building energy performance calculation, there are discussions about monthly versus hourly methods, and how far we detail the description of technical system, things about building and system zoning, building automation and control, because we want buildings that are more and more efficient. That means also more and more complicated. So this has consequences also on the calculation of a specific part of the building, such as a heat pump, which is extremely sensitive to operating conditions. So what should a calculation module for heat pump do? And here you have a simple schematics. You have your calculation method for heat pump, and this is input data. So typically the duration of the calculation interval. You know, not the climate directly or this kind of information. You know that you are asked to provide an amount of kilowatt hours for heating, for probably cooling, for domestic hot water in a given calculation interval, and with given operating conditions, for example, a required living water temperature. And this is calculated by other parts of the calculation, taking into account system control options and product data. And of course, there is a strong link between the data and the calculation procedure. Of course, the data shall fit to the calculation procedure, and the calculation procedure shall fit the right data. Otherwise, it doesn't work. And you produce this kind of output. So typically driving energy, auxiliary energy, and possibly the fraction of load covered by the system, since you want to make a lot of consideration about, for example, energy exchange with the network, the grid. So you also have to know how much you can cover, what you can do. So the scope is a calculation interval. not the season. So typically the module is focused on a calculation interval. And the possible combination of the input data can be often very far from what are assumed average conditions. For example, when you are rating a device with average assumed operating conditions in the building. And this is a big challenge. It's one of the big challenges, the sensitivity of heat pumps to operating conditions. We all know that temperature of both sources, of course, is important. And this implies that you need calculation method for this. This is outside the heat pump module. For example, you might use external temperature. So now it's climate, it's quite easy. But a ground heat exchanger is more challenging for the calculation. And also the calculation for the hot source temperature. And this, in the case of water-based system, for example, you have to calculate how is your distribution system operating, for example, at which is a required living water temperature, to make it short. But of course, also part load operation. And here you also have the effect of, is it continuous operation at reduced power because you have an inverter, but it's limited by a maximum turn down. And then you have on-off operation, if it's an on-off heat pump, but it could be also on-off because you are below the minimum continuous operation capacity. And one thing more, it depends also not only on the part load, but also on the cycling frequency. And this is, again, a complicated interaction of your heat pump with the surroundings. And I don't think so many calculation methods go into these details, but they are important, as you have seen in the first slides in about the previous part, where you saw the difference of testing a heat pump at constant operating condition or in on-off operating condition with the same temperature of the source and the sink. And then other influences you might have also, because you have also you could also have auxiliaries not included in the COP testing. Think about raising groundwater and things like this. So the sensitivity is quite high. So it's just a picture to highlight this fact. And you can see this is a typical diagram where you see the COP of a machine at full load. It's an air to water heat pump. This is the outdoor temperature. And there is one curve for each living water temperature. And you can see at 7 degrees outdoor temperature, which is a common average temperature for mild climates. And you see it could be the COP from 2.8 to 4, just because we have a different type of heat emitters. And you see the normal range of operation, you go from 2 to 6 as a COP of your machine, just to stress the difference. Each single degree is 1.5% of efficiency, or 1.5 to 2.5% efficiency lost or gained. And by comparison, if we are used to heat, for example, for boiler, because we use boiler in the past, and here the efficiency is just in the range. If you have a good condensing boiler, if you don't make any heavy mistake, it's plus or minus 6%, 10% maximum. Otherwise, there is an issue in your system. And on the contrary, heat pump performance is a range 2 to 6 or 1 to 3, let's say, as a turn down ratio, and that's quite normal. So the problem is, where do we find enough data to identify a reasonably accurate performance map so that we can consider the operating conditions that will occur during the operation within a building? And you have some pitfalls. For example, source and sink temperature should be evaporation and condensation temperature, but very often we just use what is available, typically air and water temperature, which is not evaporation and condensation. And even part load. Just think about, what is part load? Is it compressor speed or a ratio actual capacity compared to maximum capacity in the given operating conditions? And things that even no standard, at least to my knowledge, clearly defines full load. For example, 14511 and the corresponding EN 14511 European standard and the corresponding ISO, they just say, well, so that defines the nominal capacity, which is just the capacity declared by the manufacturer, which is usually the maximum, but not always. So these are things to be clarified. And just maybe anticipating something, you all know that heat pump performance is a function of at least 3 variables, the true temperatures and the part load. and the dependency is not linear. For example, speaking about the COP, just to make another example, probably you are used to this kind of abbreviations. So A7W35 to mean that this is a COP on an air-to-water heat pump running with 7 degrees outdoor air and 35 living water temperature. But to be more complete, you should also specify, well, working at 60% load. Otherwise, you still have something changing. You're not complete. There is an understatement here about the actual load to characterize correctly the COP that you declared. So just to see how it varies. And this is just a very quick example of these subtle differences, because this is just simple air-to-air heat pumps, and you see all the temperatures involved, the most important temperatures involved. And yes, usually you say, I'm working 7 to 20, because it's external air, internal air. But the heat pump actually sees the evaporation 1 degrees and 32 degrees of condensation temperature. This is relevant for the operation of the heat pump. And some calculation methods are just going from this one, from the available data to the relevant, to improve accuracy, or try to improve accuracy. And this, you can see here, for example, another hidden complexity, which is quite relevant. You see here a full load operation for an air-to-air heat pump. And of course, if you modulate down, you know that an air-to-air heat pump will increase its efficiency. Basically, because if you just slow down the compressor, you will reduce the temperature difference of the air across the condenser, so that will reduce your condensation temperature. But if at the same time you're also slowing down the fan on your indoor unit, your condensation temperature raises again. If you do the analysis, here you can expect a theoretical COP increase of 83%, and here you can anticipate that it will be only 21%, and this is quite relevant. And you could think about, is this taken into account in testing and calculation method? This is just to say that there are really a lot of things to be taken into account in a very various world, because we say heat pump, but actually then you have to consider you might have several. Now it's called external connection, because if it is heating and cooling, it could be a source and a sink, traditional words, but the external connection could be air, external air, exhaust air, solar assisted, water, ground heat exchanger, but it could be also groundwater or surface water. Then on the internal connection could be air, direct expansion, or water. And then you might introduce capacity control, integrated appliances with other services, the operating principle, vapor compression absorption, simultaneous heating and cooling, and sometimes de-superheating to recover some heat at high temperature. So if you make all the possible combination, you see something very various and different data, product data needed to characterize the machine. So this is a most important pending issue. The connection between product data and building energy performance calculation, because if you have a calculation procedure, you need an input data set. These two things you cannot separate. They must be combined. And this is a problem, because you can imagine, since the performance is so varying, you need quite a big amount of information to be able to accurately and exhaustively map the energy performance. And of course, we have to reach a balance between accuracy, exhaustivity, and the cost of finding out the product data. And this is something which is ongoing work. Until now, most of the effort has been to characterize product rating, and with such information like SCOP or IPLV, for example, for the States, which is quite a different story. In fact, this is just for the EN context, and you can see that, of course, you have here the standards involved for heat pumps. You have the product standards, which includes the testing procedures. You test products, you produce data, and you use this for product evaluation as such. For example, rating, labeling, CE marking of the heat pump. You need data for product sizing, for example, for this standard, for this EN standard, and you need the data for our context, which is relevant today. So product performance within a specific context, not as such. And here, this standard, the EN 14825, specifies the test conditions which are relevant and useful for its model. This didn't happen, unfortunately, for the energy performance calculation standard. So here, coordination, of course, is needed and hopefully is now ongoing. And this is just to list the differences between building rating and product rating. These are really two different contexts that require different data, because this gives you access to a building market, so building permit, or for example, energy performance certificate, something like this. This gives you access to product market. So the end of this process is on the shelf of the dealer, and then everything is finished because the product is sold. And this looks for the performance of each product in building specific and changing operating condition, if it's building rating. And here you try the performance of all products in the same operating condition, because you want to compare products. The question could be, are they representative? Then here you need parameters. Since you have several influences, you are interested in some parameters that allow to take into account deviation from a reference or tested conditions. And here you need a single performance indicator, one figure, because we want to rate the product on a scale. And then here you have to distinguish between the effect of the product and the effect of the systems. And here, effects of the system are embedded in the testing. And the more you embed, the more difficult the testing. You can see this with load-based testing, which of course is trying to be more representative and embedding properties of how it's operated, how the product is operated. And then here you have also to foresee the effect of bad products, wrong sizing, everything like this, because you want to compare also in practice what happens if you improve your installation. So just to see, as these are really two different contexts, so building rating and product rating. And up to now, this was the biggest effort. It was a little bit less and obliged those writing building energy performance calculation to rely on the available data set up to now. So the current challenge is using the currently available data. So this is just information that I already provided. So you will have the presentation as a remembering. So, and using the currently available data is not really satisfactory, because of course you have to go down to compromise, and you make a lot of assumptions, and all assumptions are flattening the evaluation of products. So all products are the same when you make a common evaluation. And common approaches. So what happened? You can see at all we will see very briefly at all the calculation methods that are available now. And I think some common approaches emerged. So starting from a declared performance in a single or maybe in several reference operating conditions, then you interpolate and then apply independent correction for each influencing factor. So first correct for temperatures, then correct for load, then correct for something else, and you assume they are all independent. The other way of doing this is pre-processing test results from several operating conditions, and you try to identify a characteristic function to describe the efficiency of the heat pump. Typically, you have several data test points in 14825 A, B, C, D, where all operating conditions are changing, so you're not able to extract the information about one influence factor, and you say, well, the efficiency, the exegetic efficiency will be a function of just the required output capacity. So you can calculate this function and by a pre-processing and then use it to calculate any operating condition. But this has, of course, very heavy assumptions. Or you can just use, for example, a seasonal efficiency, the weighted average of efficiency for a set of part loads. So these are just to try to see which are the most common types of calculation methods. And frequently you use additional assumption, for example, constant exergy efficiency. This is very often used for small extrapolation or interpolation. And for example, you can assume that approach of evaporator and condenser, the temperature approach, the temperature difference across an evaporator or condenser is a linear function of instantaneous capacity, for example, to switch from the available temperature to relevant temperatures. These were the common approaches, and I will try to illustrate very briefly with some examples. We'll find, of course, more details in the report. And I was dealing with EN 15316-4-2, the European standard. It's an ongoing work. It's a new draft, so this will be and just because we have to rely on existing data, there are two calculation paths which are intended to support two different sources of data, EN 14511 and 14825. Typically, capacity and COP at full load for path A, and then you correct according to part load, and then AN 14825, which is declared COP at various load and operating conditions. And you can see here the general structure. And of course, a calculation module is not only calculating a COP, it's also taking into account the product type, the product data, the required heat output for each service, source and sink temperature. Then you calculate the maximum capacity in the operating condition. You handle priority, for example, between heating and domestic hot water, and maybe also cooling. And then you correct performance according to actual operating condition. The orange parts are those which are path specific. So depending on the type of calculation that you choose and of the available data. And then at the end, you calculate backup and auxiliary energy. And these are done in two different ways. The first way, path A, you start from a performance map at full load. So here you see external air temperature and COP for different, and the COP for different living water temperature, and you can read this. And this is a map which is either declared, fully declared by your manufacturer, or which is built starting from one seed value, and then you extrapolate a default map. This is, for example, what is done in the French regulation. And very often, for example, you can see one issue, for example, here quickly, that usually you have testing points for heat pumps in this area, so cold temperature, and very few remember that you use this heat pump also for domestic hot water, so you would need at least one testing point in the area of summer temperatures. This very often, this manufacturer declared. So you start from this full load, so COP at full load, and then you correct for part load. So this is the load ratio comparison between the actual capacity and the full capacity at the same operating condition. And here you can read your multiplier. 1 means it doesn't change when you are at full load. Okay. Then usually when you decrease the load, you have a small increase and then it will decrease. And this depends on the heat pump technology, of course. That's the difficult part of path A, where you have to, where there are several different possible options. What you see here is just a default option. And so this is just to remind the general rule. You start by COP at 100% for the given source and sink temperature, because you have a map or because you created a map based on a single seed value, and then you apply a correction to your COP to take into account part load operation. That's really the basics of this method. And this is instead path B. In this case, it is first a pre-processing. You have performance in 4 points, but I will do this. I will explain this on another sheet on this slide. You can see here in the 4 points, you have 4 operating points at very different operating conditions. So you calculate the exergy efficiency, which is here, which is a ratio between your COP and the theoretical Carnot COP. And you assume then your exergetic efficiency is just a function of the output power. So you use the 4 points to identify this curve. And then you say, okay, I ask for 2 kilowatts. So I can read here my exergetic efficiency. I take into account my operating conditions. I know my COP in actual operating condition, very basically. Of course, this is a really strong assumption that exergetic efficiency depends only on the output power. Probably you shouldn't use several of these curves and then somehow interpolate, but this will be future discussion. And just to know, one of the possible limitation, of course, in testing the product, you use these 4 points. Here you can see the testing points for the 14A25, the point A, B, C, D. This is the outdoor air temperature, and this is a living water temperature when testing air to water heat pumps, and this is a part load ratio. And if you compare with the performance map before, you can see that the testing points are really positioned on an ideally sized and very well controlled system going down at very low temperature. Even the 55, for example, you go down to 30 degrees living water temperature. So you could question about, is this representative if you are operating on this part of the performance diagram? And this is a question about the compromise between the number of data and the accuracy and exhaustivity. I mean, by exhaustive, covering all the possible operating or possible and, of course, likely operating condition. But think about just using this heat pump on, for example, fan coil. You would use a constant flow temperature, not, of course, not a decreasing living water temperature. So just to mention the calculation procedure. And of course, there are quite similar examples. If I go in Italy, Unit ES 11300 is just path A. This is the grid of temperatures. So in Italy, we included also some requirement about temperature in summer operating condition, and we use the 4 COP correction factors, just the default curve. And of course, this is maybe okay for air to water, for example, but for air to air, this is not enough, definitely. So nothing is perfect, nothing is complete. We'll see this in the conclusions. And here you can see in France, for example, they also use path A, just the same method, and they use a seed value. So you have your COP, 735, and you have multiplication coefficients, which are default. And to calculate the next value of the map, you just apply these fixed calculation multiplication factors. Of course, this is flattening all products. And of course, they are all the same in this case. United Kingdom use another approach. They pre-calculate the seasonal COP according to a plant size ratio, which is an indication if your heat pump is oversized or downsized or undersized compared to your system. So you just estimate your plant size ratio and then take into account is it floor heating, radiators, convectors, and you select your seasonal performance factor. It's actually a seasonal calculation in this case. Here you have another example of simplification and bearing a lot of assumptions. What about Energy Plus? Energy Plus simply asks you, give me the performance map. That's it. Because in fact, the power input is your reference tested input multiplied by 3 correction factors, which are just polynomial equation. So you have either to ask the manufacturer to tell you all the factors, or you must do some curve fitting on the available data. So it's not really much supporting. These are just sample equations. There are also some default values, but they are from machines from several years ago. Canada, NECB in Canada is quite similar to the method about Energy Plus, but in this case you have default values that are provided by the regulation depending on your heat pump type. So in this case, this is a value for an air-to-water electric compressor-driven heat pump. Okay, conclusions. So I conclude, sorry for the delay. So heat pumps are damn sensitive to operating conditions, at least free and non-linear, with a result in the range 1 to 3. So it's dramatically important to cover the performance map. There are a huge variety of heat pumps typologies we've seen, and there are differences in the calculation. The product standardization up to now focused mainly on the product rating, and countries have maybe different prevailing needs, type of heat pumps. Building energy performance calculation requires very various situations, much more than what is anticipated in just rating a product. And given this variety of heat pump types and in the absence of well-defined product standards, the energy performance calculation standard had to adapt. And input data and method are interdependent. So if you want to solve the situation and progress, there must be a lot of communication between the building energy performance people and the heat pump people. So that's huge work in progress. And hopefully this is maybe occurring at least in the European context. I hope everywhere, because it's important to collaborate, because data is needed. Of course, it's a cost, but we need a minimum representation of the performance map to be exhaustive and accurate enough with the calculation of the building. Okay, thank you. That's all from me, and let's see if there are questions. Thank you.